The topic we are going to cover in today's class is boundary value problems. And the method we are going to learn and use for solving boundary value problems is called finite difference method. There are other methods as well, but today our scope will be limited to the finite difference method only. Okay, let me first explain how the method works briefly with an example. Let us consider a very silly problem, very simple looking boundary value problem. I hope all of you already know what a boundary value problem is, right? The boundary value problem is a differential equation along with conditions involving 2 points. Say this is a very standard but simple boundary value problem. We are given a second order differential equation. We have 2 points involved in the conditions given, the point x equals to 0 and the point x equals to 2. Now, basically the idea behind boundary finite difference method is replacing y dash. I mean, what we are going to do is divide the, say this is 0 and this is 2. Maybe this is the solution function. What we are going to do is divide this interval into sub-intervals, preferably of equal length. And say this guy is xi, x1, generally starts with x0. So say this is x0. The second point is x1. The third point is x2, and so on. The last one is xn. So there are n sub-intervals. So the grid, there are n plus 1 grid points as usual. What we do is generally replace y dash in our given equation by yi plus 1 minus yi by h, where h is the sub-interval length. But who's I mean yi, not yi, but who is yi? Yi is, if this is xi, then this is the exact value. Say this is the y axis. So let me use another class. So this is the exact value of the function. But as you already know, in differential numerical methods to solve differential equations, what we do is actually approximate the value of the y using some suitable formula or something. So yi is actually the approximation at xi. So this is yi. So at each xi, the approximate value of y is yi. So you already know what yi prime should mean. It means the value of the slope of the tangent drawn at xi, but the approximate value of it. So we are approximating the slope by this already well-known formula, right? And there is another, if you go further and try to find a formula for yi double prime, you can easily find yi prime minus yi prime by h. And if you substitute the expression of yi prime and yi plus 1 prime, after simplification, it becomes yi plus 1 minus 2yi plus yi minus 1 by h squared. So these two are approximation for first and second derivatives of y at different grid points, right? So the main idea is replace the derivatives by these guys in the original equation. So what we get is yi. First of all, we are rewriting the equation for individual grid points, right? So this is what we are going to do. That means this guy is actually y naught, and this guy is actually yn. The first and last y is already known from the boundary conditions. And if you replace yi double prime by the formula we just wrote here, we get yi plus 1 minus 2yi plus yi minus 1 divided by 8 square. There is no yi prime in this particular example, so we do not have to put this. But if you had, you had to, if you had such a term, you had to replace by this expression as well, right? Minus yi equals to 0. If you simplify this equation, this becomes actually, let me write the simplified equation, multiply 8 square on both sides. And so finally, we would get yi plus 1. You have a yi here, another yi here. So finally, you would get 2. If I am not making any calculation error, I should get 2 plus 8 square yi plus yi minus 1 equals to 0. So now all we have to do is consider a suitable value of 8. So our interval is from 0 to 2. For the sake of simplicity, let's choose a a large enough 8. Say, for example, 8 is, say 8 is 0.5. Let me rewrite the equation here. Yi plus 1 minus 2 plus 8 square yi plus yi minus 1 equals to 0. This was the equation. And we are, where is 8? Okay, here is 8. We are choosing h equals to 0.5. So technically, this is 0, this is 2. So this is 1, this is 0.5, and this is 1.5. So technically, this is x0, this is x1, this is x2, this is x3, and this is x4. So in our case, for h equals to 0.5, n is actually 4, right? So what we can do is put I equals to 1, 2, and 3 in this equation. Putting I equals to 1, we get actually y2 minus, the value of h is 0.5, its square is 0.25, so 2.25 y, y1 plus y not equals to 0. For I equals to 2, we get y3 minus 2.25 y2 plus y1 equals to 0. And for I equals to 3, we get y4 minus 2.25 y3 plus y2 equals to 0. Please correct me if I am making any calculation error anywhere. Now, we must notice that we already know what y0 and y4 is from the last page. This is y0 and this is y4.
Sir.
Okay, yeah.
So in the previous page, I had a confusion regarding the last part.
Yeah, where?
Yes, sir. So we wrote yi plus 1 prime as yi plus 1 minus yi, I think. And then we again got minus yi plus yi minus 1, like in this part, right?
Okay, this guy is literally this expression, right?
Yes.
Now, we do not have a direct expression for yi plus 1 prime, right? But you can just replace I by I plus 1 here. Do you get the idea?
But that would involve a I plus 2 term, which is not present here in the expression.
Okay, I think I got your point. Okay, there is this idea. Okay, I got your point. Let me explain what I did there in a separate page. Generally, when we try to find the derivative of a point numerically, so this is xi, this is xi plus 1, and this is xi minus 1. So say we do not have the actual equation of the graph, but we have these 3 points and we want to find the derivative at xi. There is two school of thoughts. There are two school of thoughts. One is this slope of this line. You can understand that both of the interval length is h here. So one way is use the next point to approximate the slope by finding the slope of the direct straight line, second line connecting these 2 points. Another school of thought is connect these two. Use the point just left of it. Use the point on the right or use the point on the left. You can use either one. Uh, there are actually, if I am not wrong, there are names for these formulas: forward difference formula and backward difference formula, if I'm recalling the names correctly. And when you are dealing with the problem of finding second derivative, there is another school of thought that is probably, as far as I can recall, it's called central difference formula. And you can use central difference formula for finding first derivative as well. Just skip xi completely and find the slope of the line connecting these two values. You can use either formula depending on the situation or depending on your choice. All right. Now, in this case, maybe use forward difference formula for finding what. Okay. In our case, replace yi prime by the forward difference formula, but replace yi plus 1 prime by the backward difference formula. Now, this may feel a little bit, informal to you, right? Choosing different formulas for two different terms here. But there are even more rigorous proofs for all of this using Taylor series, all right? So you can search them in any numerical method books. Most of the books cover them. So what we do is, you know the Taylor series formula, right? Now, what we can do is approximate f prime x by truncating here and making f prime x subject, right? What we also can do is replace h by minus h to get a different formula that looks like this. Then this one is the forward difference formula. This one is the backward difference formula. Now, what you can do is add these two equations. If you add these two equations, you get this guy plus this guy here. Okay, let me write it. F of x plus h plus f of x minus h. And these two gets cancelled, so we have 2f of x. But these two gets added up, right? So plus h square f prime x, and let's truncate the remaining terms. Now all you have to do is make f double prime x the subject. You can understand that if we consider f of x as f of xi, then what should f of xi minus h and f of xi plus h be? The next and the last points, right? So this is just xi plus xi minus 1, and this is just xi plus 1. And after passing through the function f, these guys become y. So this term is actually yi plus 1. This term is actually yi minus 1. This is yi. So you got an algebraic proof for the formula, right? So there are multiple ways to reach that formula. You can use either of them, any of them, right? Are you convinced?
Yes, sir.
All right, okay. Let's get back to our where we were. So we have put I equals to 1, 2, and 3 and got these three equations. What I was referring is we already know what y naught is. We already know what yn, or in other words, in our case, n equals to 4. So we already know what y4 is. So we can replace y0 by our known value 0. We can replace y4 by our known value. What was that? A very weird value, right? 3.626686. 3.62686. After substitution, you get a system of linear equations. There are three linear equations. Uh, there, there were actually from y0 to y4. Initially, it appeared that there were 5 variables for these three linear equations, but we already got the value of y0 and y4. There remain y1, y2, and y3 only, right? So we have an equation. If you do not like decimal points, you can multiply by 4 on both sides, etc. Anyway, finally we have three equations, a system of linear equation. We can solve this system using any known method, and finally we would get eventually. I'm not going through the solution process, but eventually we would get y1 equals to 0.52635, y2 equals to 1.18428, and y3 equals to 2.13829. Okay, technically, these example problem does not really belong to our lab 2 course. This belongs to actually the numerical method course, but I introduced this simple example to explain how the finite difference method works. Please let me know if there is any question regarding the finite difference method. All right, if there is no question.
So
Now,
how did we evaluate the values for y1, y2, and y3?
you can use any method. For this particular example, there are three. This is a system of three equations only. So this is CD to solve. We are going to explain how we deal with larger systems. Okay, but for this particular example, for now, you can use any known method you want. Okay.
So we will treat it as a system of linear equations and solve it using linear algebra.
You can solve it using any method you want for this particular example. But when we are going to write the code for finite difference method, we will have systems that are way larger than 3 by 3, right, in size. So for those, we are going to use methods from linear algebra. But for now, for this particular silly problem, you can use any known methods from high school, right? I haven't gone into the linear algebra part yet. We will eventually go there, all right? Okay. So the boundary value problem here was, as you can see, this is the linear differential equation. This equation is linear. You can understand that if this equation was non-linear, we may face a little bit of problems, but we will see later. For now, let me share a PDF I created. Okay. This is the equation you can see on screen is a linear, general linear. This equation is actually a general linear differential equation of order 2, right? So finite difference method act a little different for linear and nonlinear equations. First, we are going to learn how linear equations are solved using finite difference method. Later in today's lecture, we will see how we use finite difference method for nonlinear differential equations. So this is a differential equation so far, but if you are given two boundary conditions, for example, y at y at a is alpha, y at b is beta, then it becomes a boundary value problem. So the boundary points are x equals to a and x equals to b. We have a coefficient for we have a coefficient for y prime. We have a coefficient for y, and basically the original equation look like this, you can understand y double prime equals to p of x y prime plus q of x y plus r of x. We have already used the subscript I uh, as the to introduce the grid points, right? Now, as you have seen from this silly problem we solved using finite difference method, you can see if we slightly if we rewrite this equation, this system of equations, let me write in this box here. It looks like this: 2.25 y1 minus y2 equals to 0. The second equation is y1 minus 2.25 y2 plus y3 equals to 0. And the final equation is y2 minus 2.25 y3 equals to that weird number 3 point, let's write the number below this line, 3.62686. So you can see that the system has a pattern, right? The index is shifting one place at a time in each equation. So in a way, you can see that for this particular situation, you are never going to get an equation that involves more than 3 variables. Even if the system, even if the number, even if n were greater than 4, maybe even if n equals to 100, you can see that here we have I minus 1, I, and I plus 1 only. So for any value of I, we are going to get exactly 3 variables in each equation. And the final equation would always look like this. Let me go to the PDF. The final system of equation would always end up looking like if we write in matrix form, actually, the final system of equation is always going to end up looking like this. Basically, in the first row, let me show you step by step, actually. So we have already given 2 variable values, the first one and the last one. And if you substitute by the formula we have given for y prime and y double prime, this is the formula for y double prime, this is the formula for y prime. Finally, we would get equations like this. You may wonder why we have this formula here. This is the central difference formula for y prime. So we have, for each equation, we have 3 variables: wi minus 1, wi, and wi plus 1. So after simplification, we would get something like this: some coefficient times wi minus 1 plus some coefficient times wi minus 2 plus some other coefficient times wi. Where does w minus 2 come? This is just wi. And finally, some other coefficient times wi plus 1 equals some number. So if you keep putting I equals to starting from 1 to n, we would get n equations, right? In those n equations, basically, the last variable would be n plus 1. So that is why they indexed n plus 1 here. So they are considering the last point to be n plus 1, but not n, for the sake of having simpler system of equations. So if you keep putting I equals to 1 through n, you would get n equations involving n variables from w1 to wn. But the final system would look something like this. Okay, this is the one after simplification. This is the one after simplification. You can see that they simplified the coefficients for wi minus 1, wi, and wi plus 1 as well. And this can be done by just doing some algebra in this. So after simplification, we get this. And if you keep putting values of I from 1 to n, you will eventually get a system that can be written as matrix form in this way. The matrix form is AW equals to B. You are familiar with this form, where A is this matrix. These are just the coefficients we got from the simplified equation. And W column vector is the variables, contains the variables, and B is the right-hand side in the simplified equation, right? So this system would always look something like this, where you have a band of non-zero values here, but the remaining values are all zeros. And this band, there are three kind of this one is the main diagonal. Let's call this guy and this guy semi-diagonals. So we have one major diagonal along with the adjacent semi-diagonals. So three diagonals containing non-zero values. Some of them may be zero coincidentally, but in general, we expect non-zero values. And the remaining entries in the matrix is all the remaining entries are zero, right? So this sort of system of equations is called, there is a name for it, tri-diagonal system. Now, as Ilham already asked, he showed his concern about the method that we are going to use to solve the system. So how to solve such a system if, say, for example, n is 1000? We are going to use linear algebra here, but whenever I pronounce linear algebra methods to solve system of linear equations, the first few names probably comes to your mind are Gaussian elimination, Gauss-Jordan elimination, and matrix inverses. But this particular system has a pattern, and for this particular pattern, there is a method that gives us much simpler situation than those methods. All right, and that method is called LU factorization. Some of you are already familiar with this term, I think. Let's see how LU factorization works. Okay, before going into LU factorization, here is an algorithm. This is actually a screenshot from all the screenshots are actually from Barden's numerical method book, so you can find them there. And I'm going to share this PDF with you as well. I made this PDF just for conducting today's class in an easy way, because there are multiple pages in multiple locations in Barden's book that we are going to use today. So this I made this PDF to make my life easy. That's all. So this is how the algorithm works. There are two parts of the algorithm. The first part involves creating the system of equation, and the second part involves solving it using LU factorization that we are going to explain later. So let's see what they did. What they did is focus on this part first. What they did is for each equation, say for example, consider the ith equation here. This is the first equation, right? Focus on the ith equation. The ith equation has somewhere -1. In fact, we already have the ith equation written here. So for the ith, this is the ith equation, right? In the ith equation, the coefficient of wi minus 1 is this, wi is this, and okay, let's, so this is wi minus 1, this is wi, this is wi plus 1, and finally this is the right hand side. They are calling this guy ai, this guy bi, this guy ci, and this guy di. and they are actually saving those values of AI, BI, CI, and DIs here. So now you know the ith equation should look like this: AIWI plus B, sorry, WI minus 1 plus BIWI plus CIWI plus 1 equals to DI. And they're doing it for I equals to 2 through n minus 1. So for each of those equations starting from I equals to 2 to n minus, ending at n minus 1, they are creating kind of arrays, right? Now, the only problem is the first and last rows are different. The first row and the last row, or I mean, the first and last equations are different because there are only two non-zero entries in the first row and same for the last row, because we already know the value of y naught and yn, right? And for the same reason, the di is different for the first and last row as well, because that known value of y naught and yn are going to be treated as the right hand side constant. So that is why what they're doing, is creating the first equation and the last equation separately. So up to this point, all they did was stored all the coefficients for each of the equations. Now, after step 3, we have a system of linear equations which has a particular pattern for which it is called tridiagonal system of linear equation. Now, as I have already said, that when a system looks like this, the A matrix, the coefficient matrix contains a band of 3 non-zero diagonals only. There is a method called LU factorization, and this is how the method works. Say, for example, most of you already should know what an LU factorization method is, but let me explain briefly. For any matrix A, forget system of equations. For any matrix A, you can express the matrix as a product of two matrices, name them L and U, where L is a lower triangular matrix and U is an upper triangular matrix. In general cases, these entries are not zero. For any general matrix A, these entries here are not zero, and these entries here are not zero. In case of a tridiagonal matrix, we can consider these guys already to be zero. You can understand that, I hope. What we can do with is consider the diagonal of the U matrix all ones and the upper triangular values non-zero. And for the L matrix, the lower triangular entries are all non-zero, including a diagonal, and rest of the entries in both matrices zero. Then we multiply these two matrices, L times U, and we equate the matrix with the general matrix A. So we have this situation: multiply the L in next page with U and equate it with A, and basically compare each element position by position from left hand side and right hand side and equate them. Why do we equate them? We equate okay, where were we? So if you multiply L and U, equate with A, and compare all the position by position elements from left hand side and right hand side and equate them to form a huge number of equations to actually solve for these non-zero entries. And eventually you will find your L matrix and U matrix. This is how the LU factorization method works. But in our case, the LU factorization method becomes a very easier version of itself, because the uh, outside of these three diagonals, all the entries are zero in the A matrix. That is why even the L and U matrices looks very simple. There are additional zeros here and here, making our life even further easier, right? So what we have to do is multiply this simple L and this simple U and equate with the A matrix given in our last page, and compare the elements position by position on both sides, and this will eventually give us this system. So from this equation, L11 is directly available. From this equation and this equation and this equation, we will get the remaining values of L and U entries. So once you have the L matrix and U matrix, solving a tridiagonal system becomes easier. Let me show you why. So you have, originally we had a system of linear equation Ax equals to B. This is what we started with, right? And somehow you expressed this matrix as a product of two very simple looking triangular matrices with a lot of entries zero, right? So what we have now is LUX equals to B. Now simply consider U times X to be some other vector Y. Then we have a system Ly equals to B. Now this equation is very easily solvable just because of the fact that L is a lower triangular matrix. So it kind of auto solves itself. Just use back substitution and all. So you can easily solve this system to get the values of y's. Now you have the y vector, so you can just use this equation. What we used here is ux equals to y, right? This was the substitution we used. Now, since you have y, you have the right hand side of the system, where here the matrix is an upper triangular matrix, and this one is also very simple. So you can also solve this one pretty easily. Solving these two systems is way more easier than solving the original system. All right. So that is why we prefer using LU factorization method while solving the system of tridiagonal equations in finite difference method. All right. So let's get back to the finite difference method. And here is the, okay, here is an algorithm uh, for finding the L and U matrices. So it actually is pretty straightforward. The first and last row gives us these two, and the rows in between gives us this system. You can iteratively use these equations to find all the entries of L and U matrices. But we are not going to use this algorithm separately. Rather, we are going to integrate it into the algorithm of finite difference method. So this was the finite difference method algorithm, and as I have already mentioned, up to this point, we just created our system. Now, in the later block, we are going to solve the tridiagonal system using LU factorization. So this is the algorithm that does exactly that. So get the L and U's and solve for the system to get Wi, and that Wi's are actually the y values at the grid points xi. So this is how the system actually works. Please let me know if there is any questions so far. If there is no questions, then we shall move on to nonlinear finite difference method. All right. So solving a linear system, linear boundary value problem was slightly easier actually. This one is, sorry, this one is non-linear. Non-linear boundary value. So as I was saying, linear one was slightly easier than this one. Here, in the previous case, we wrote y double prime equals to some p times y prime. P is a function, of course, of x plus q times y plus r, right? But here we do not have the luxury to write the expression on the right hand side in this form, because the right hand side may be of non-linear structure, and there are infinitely many ways you can have non-linear structure. Linear structure has this fixed general expression, but there is no such general expressions for non-linear cases, right? There can be infinitely many forms. That is why all we can write is a general function f that may or may not contain all of x, y, y prime, right? And this part is just like before. We have an initial point A and a final point B, two boundary points, right? And we know the values of y at those 2 points. Now, how is this uh, uh, problem going to be different if we attempt to solve using finite difference method, right? That's the question. You can understand that the procedure is similar. Just replace y prime by the expression, y double prime by the expression, and finally, eventually, you would get a system just like this. This is also kind of, I mean, not exactly, but kind of a tri-diagonal system. Uh, Not exactly, actually. Let's forget the word tri-diagonal system now. This is actually a system of nonlinear equations. The tri-diagonal system in case of linear equation, differential equation, we got was a tri-diagonal one. Here, we got a nonlinear system of equation. Now, you have learned methods of solving nonlinear system of differential equations. There are many. You must have learned in numerical method and lab 1. But here we are going to use Newton's method. Now, what is Newton's method for solving system of nonlinear equations? Even if you do not understand how the Newton's method for nonlinear system works, you must know how the method by Newton-Raphson works for linear system of equations, right? The governing equation is xi plus 1 equals to xi minus f of xi by f prime of xi. A very favorite formula for us, right? Okay. Now, this one works for a single variable, but we have a system here. This works for a single variable equation, and of course, the equation can be as nonlinear as possible. Doesn't matter. The method does not mind. Here, we also have a nonlinear situation, but the difference is we have multiple variables involved here. The equation in this box is written for single variable. What we can do is just look at this formula and generalize it just by observation, and this is how we can do that. In our case, xi plus 1 is not a single variable, but a collection of variables, or in other words, a vector. So xi is going to be a vector as well. Now here is a problem. What is f of xi by f prime of xi? Basically, the system we are trying to solve is f1 of x1 up to xn equals to 0, f2 of x1 up to xn equals to 0, and finally at some point, some fn of x1 up to xn equals to 0. This is the kind of system we are trying to solve using Newton's method. So when we write f of xi for the system, but not for the single variable, we are meaning that we are evaluating each function at the point xi, which is an n-dimensional point. This xi vector is an n-dimensional point, but you must remember that we do not have a single function f, but a collection of functions. So this is a vector as well. So the final outcome is a column vector. Now, what is f prime for multivariable? You must know from real analysis that derivative for multivariable is simply the Jacobian. So what we have here is inverse of f prime. So we must have inverse of the Jacobian matrix evaluated at the xi vector. So here we have an n by n matrix here, and here we have an n by 1 column. After multiplication, this is going to produce an n by column. So this is also an n by 1 column. So we can complete the subtraction and get our new iteration value, new variable. This is the old variable value. This is the new variable value from the Newton-Raphson method, right? So we are going to use this equation to iteratively get better approximations for xi, and eventually at some point the final result would be within some tolerance limit. So you already understand that there is a major difference between the linear and nonlinear finite difference method. In linear finite difference method, our solution was exact. Exact not in terms of the solution of the boundary value problem, but in terms of the system of equation. The solution of the system of equation using LU factorization was an exact solution of the system. But here we are using an iterative method. So our solution for this system is not going to be exact, but an approximate one. And we can approximate with whatever tolerance we assign, right? Please let me know if there is any question so far. Okay. So if there is no questions, then let me go to whiteboard and show an idea. The equation we finally got for Newton's method was Jacobian matrix evaluated at the xi vector's inverse times f of xi vector. Now, here's the thing. If we try to solve the system using this iterative method, we have to calculate the Jacobian inverse in each iteration. And on top of that, we are going to need to multiply it with this column matrix as well. F is also a vector. So there is a lot of computational complexity involved in evaluating inverse matrix at each iteration. So we are interested in finding an alternate to this, inefficient algorithm. So what we are going to do is consider this guy, this part to be equal to something like, say, Vi. Not this part, but this part including the minus. So what we have is xi plus 1 equals to xi plus v plus vi. This is what we have now. So if we somehow manage to find vi, we can just add it with xi to get our new approximation xi plus 1. But how to find vi? You can understand that if you make f of xi the subject of the equation, this equation, only this part then it becomes, this is equal to Jacobian, the inverse Jacobian becomes Jacobian on the right hand side. So Jacobian evaluated at xi times vi. So we have, if I rewrite the equation one more time, we get this. So this, as you can see, this is a system of linear equation. So vi, the variable vi contains vectors like v1, elements like this. So this is a straightforward system of linear equations. And we can solve this system of linear equation using LU factorization again. So here is the general, they already have all the functions f1, f2, f3 here. So they calculated the they actually simplified the general expression ready for us of the Jacobian. And this is the system I was talking about. This is the Jacobian times the v vector equals to the right hand side where we have all the functions. The right hand side was, I think I made a slight mistake in here. I had a minus sign here, right? So that minus should be here, and that minus should be here. So the right hand side is negative of all the functions. As you can see here, this the negative sign is here, and this is the f1 function, this is f2 function, and so on. So they actually introduced again a system of linear equations, and this system of linear equation can be solved using LU factorization. And this is the algorithm for nonlinear. Okay, this one is for nonlinear. So nonlinear finite difference method algorithm. And this is what they did. Uh, you can see that in case of linear, there was no loop involved. But here we have a loop starting from k equals to 1 up to m, where m is some maximum number of iterations you decide at the beginning of your code. So the entire idea is executed inside a loop, and the loop is for steps 5 to 16. So step 5, 6, and 7, you can understand that step 5, 6, and 7 involves creating the system just like linear finite difference method. Step 8, 9, and 10 actually are for solving using LU factorization. Step 11 is that Wn equals Wn plus Vn, the line we wrote at the end of our argument here, right? This line. So in steps 8, 9, 10, they solved for Vn. In step 11, they added the Vn with Wn to get the better approximation. And finally, they are introducing the idea of tolerance here, when to stop, and they are repeating the entire process in a loop, repeating from step 16 going back to step 4, because we are actually approximating the solution of the system using Newton method, right? So that is why entire idea is inside a loop. Finally, we at some point we write the output. So this is how the nonlinear finite difference method works. That was the overall idea. Please let me know if there is any confusion in it. If there is no confusion, then I am going to provide an assignment after today's lecture on finite difference method, the linear one. I'm going to post the assignment later tonight, but since most of you are present, let me discuss the problem here already. Uh, I will provide a linear boundary value problem. You have to solve it using finite difference method. Since the equation is linear, you have to solve it using the linear version, right? And I will see what I can do for the non-linear part. But for now, your assignment, your offline assignment will be actually solving a linear boundary value problem using the linear finite difference proof. I will post the problem probably within half an hour on this call. So that is the lecture for tonight. We will see you all on our next class. If you have no more questions or confusions.
Sir, did you receive the email about the exams?
Yes, we received the email about exams. We have talked about. Okay, I think. Please let me stop the recording here.